Hello, this will be a video covering waves, including transverse waves, longitudinal waves, waves going through different mediums and going between mediums, interference, reflection, standing waves, as well as resonance and harmonics. Okay, so first, let's start off with the two really big types of waves that you'll see. First, you have transverse waves. So, transverse waves, uh, transverse waves are waves that you see moving like up and down. So what it means is like, um, when you look at the surface of a water and it has ripples, that would be like a transverse wave. Or when you look at a string and it's vibrating back and forth, um, that would also be a transverse wave. And the vibration of a transverse wave is going to be perpendicular to its direction of travel. And so when you have a wave traveling, like on this graph here that I'll draw, it'll be traveling from left to right, but the wave will be vibrating um, up and down like this. So it looks like a sine wave or a cosine wave. Um, and so this is a transverse wave. And then examples of transverse waves that you'll see will be like light. When you view light as a wave, it would be a transverse wave, or like I said, for like a vibrating string, would also be a transverse wave because the direction of the vibration is perpendicular to the direction of movement of the wave. So the wave would be traveling in this, like again, from left to right, but it's vibrating up and down like this. And so the motion here, um, again, motion would be up and down. So for like an electromagnetic wave for light, you would have like an electron that's oscillating up and down to create these oscillating electric and magnetic waves that are perpendicular. But that's a property of light. And like for a string, the individual particles on the string will be vibrating up and down as the wave travels from left to right in this case. Now, for this graph, there are a few important features on this graph that you need to know. So this center point, or like this zero on the graph here, this is the equilibrium position. Equilibrium. So when the amplitude is zero, or when there is no wave, the string or whatever medium it is, or for light, there is no medium. But when there's no wave, um, it would just be a flat line. However, when there is a wave, it'll oscillate around the equilibrium. So it's like an oscillator in that case. But again, the equilibrium position, so like for when there's a still particle, when it's not moving and it's not creating any waves, it will be at rest at equilibrium. When it starts oscillating, it'll oscillate around equilibrium, and the wave will oscillate around this equilibrium position as well. Next, we have crests. So crests are maximums of the wave. So like this is a crest, and this is also a crest, and this is also a crest. And so it's whenever a wave has a maximum. And then a trough is whenever the wave has a minimum. Now, I mentioned the amplitude of a wave. So you should know that the amplitude of a wave is like a measure of how far it oscillates from equilibrium. And the amplitude of a wave is the absolute value of the distance it goes in one direction. So it's not this total, height of the wave. It's not the maximum minus the minimum. It's the maximum or the minimum. It's the absolute value of the maximum and the minimum's deviation from equilibrium. So in amplitude here, so this is the amplitude of the wave, and this is also the amplitude of the wave. And for now, we're only going to deal with waves where the amplitude is the same on both sides. In some cases, such as like electronic signals or something, you could have a case where like you want to find like the peak to peak amplitude, which is the whole entire maximum minus minimum or something. Because if you have like a DC offset, then it won't be centered around, or like this equilibrium won't be at zero, and then so that might complicate some things. Or maybe like the wave is asymmetric, so it looks like that or something, and then it's hard to know like where the equilibrium is because you can't just say like, oh, it's the center here, or maybe you want to like have it where the areas are the same. It just gets more complicated, but right now we're only going to deal with like these symmetric waves. And so the amplitude here is the absolute deviation in one direction. And so the maximum minus the minimum is going to be two amplitudes. So each of these deviations here is one amplitude. And next we'll talk about the wavelength of a wave. And so the wavelength of a wave is how the distance it takes for the wave to repeat. So we're working with periodic waves, meaning the waves will repeat with a given period. And this period doesn't change if the medium doesn't change for now. So to find the wavelength, you find the distance between when a part of this wave repeats. So like the distance between troughs is one wavelength, or the distance between crests is one wavelength. And the wavelength is denoted by Greek letter lambda, and it's measured in SI units of meters. You can also measure the distance between zero crossings. So this here is one wavelength. And notice that I didn't go from one zero to the next zero because these are not repeats. You see that here this wave is going up, whereas at this zero it's going down, which means that these are not the same. You have to go to the same part of the wave and measure when the same part of the wave repeats to find the wavelength. And so it has to be when both are rising. And so these two rising edges, you can't just go from one zero to another zero because that's actually just half a wavelength. Or you can't go from like this point here to this point here. You have to go from this point here to when it rises back up again for the next wavelength. Okay, so now that we've labeled this wave, correct this, let's discuss a really important equation here, and that is that the velocity or the speed of a wave, the speed that it travels in one direction, is going to be equal to lambda f, where f is the frequency and lambda is the wavelength. And so frequency here is just equal to velocity over wavelength, or it is the number of waves per second. So you can think about it as like the number of full waves, um, the number of full waves per second. And so frequency here has a unit of, the unit of frequency is going to be in inverse seconds, which is also called hertz. And so this is the number of waves that happen per second. So if you have a wave that oscillates one time per second, that is going to be equal to a frequency of 1. And if you have a wave that oscillates twice per second, that's a frequency of 2. And if you have a wave that takes 2 seconds for a full oscillation, then that is going to be equal to a frequency of 1/2. And frequency is also equal to the inverse of a period, where period t is equal to the time it takes for one oscillation. So for one wave. Okay. Now, like I said before, the lambda here, Greek letter lambda, is equal to wavelength. Oh, also one more thing. Frequency, I wrote it as F here. Frequency can also sometimes be written as the Greek letter nu. So this is not V, it's not velocity. You notice usually it has like these curls, or it has to have these curls at the top of the V in order to distinguish it from the Roman letter V. But the Greek letter nu is also frequency. So you could see frequency written with F. You could also see it written with nu. But again, they both mean frequency. Now lambda here is equal to wavelength. So this is wavelength. And then, like we discussed before, this is the distance it takes for this wave to repeat. and then it is measured in SI units of meters. And V here is equal to wave speed, and that's how fast a wave travels. And now this makes sense because frequency is how many waves travel per second, and the wavelength is how many meters per wave. So if you multiply the waves per second times meters per wave, then you get meters per second, which is velocity. So v here is the speed at which this wave travels. And now for light, v is equal to a constant c. C is just the speed of light, and this is equal to approximately 3.00 times 10 to the 8 meters per second. And this is extremely fast. I think you can travel around the Earth around, I think, like 7.5 times in a second going at the speed of light. Um, anyway, it's just really incomprehensible almost at human scales. But the speed of light is an extremely important constant in physics, especially with modern physics. And so it's not exactly 3 times 10 to the 8. It's just that with 3 sig figs, it's actually like a little bit under 300 million meters per second. It's like 299 million something, but it rounds up to 3.00 times 10 to the 8. Anyways, this is the speed of light in a vacuum. So the speed of light does change based on what medium it's passing through, but in a vacuum, it travels this fast. And it is extremely important in physics. As you know, like a really famous example is Einstein's equation E equals mc squared, where c is this speed of light constant, and in SI units, again, it's 3.00 times 10 to the 8 meters per second. And now notice that the amplitude here is no way related to the velocity. Now the amplitude of the wave is related to the energy of the wave, and you think it makes sense because if you're trying to like shake a string or pluck a string, the harder you pluck it, or like the harder you shake it, the further it's going to deviate from equilibrium. And like for musical instruments, the higher the amplitude, the louder it is. So you have that intuition that the amplitude is related to energy, but it's not related to the velocity. Now let's examine another type of wave called the longitudinal wave. So longitudinal. And a famous example of this is sound. So you know that sound waves, they don't travel like squiggly lines. They travel as compressions and refractions. So sound waves travel when air or some other medium gets compressed, and then those compressions travel through the air in waves. And I will illustrate that using a slinky because it's hard to draw, particles of air, but you can find images or animations online that illustrate it really well, and it's really cool. But like, so we'll have parts that are spread out, and then there's parts that's going to be compressed, and then there'll be parts that are spread out again, and then there'll be more compressions, and then it spreads out. And so the wave travels in this direction. Let's just say you can't really tell just by looking at it, but we can say that it travels in this compression, this direction. And what will happen is these compressions will move in this direction, and they'll stay distanced the same amount apart. And that will be how the wave moves instead of so it's compressions and these refractions that are moving instead of these crests and troughs that are moving. And so, like I said here, places where they're closer together is called a compression. And then places where it's stretched apart is a rarefaction. And then if you notice here, the wave or the particles in the slinky or the medium of air or something, whatever it's moving through, these particles are moving back and forth in this direction. Like if you stretch out a slinky, the slinky doesn't move like side to side like this unless you shake it side to side. Like if you just compress it like this and send a shock wave through almost, it's going to move back and forth. So the particle moves in the same direction as the wave is traveling. Whereas for transverse waves, the particle moves perpendicular to the direction of the wave's travel. Um, Okay, so again, these same equations apply to longitudinal waves. They're just a different type of wave. But then you can even represent longitudinal waves as almost like a transverse wave on a graph if you plot like density at these different points. But anyways, they're both waves and they both periodic and they both what we'll deal with follow like this sine wave shape. But it's just two different types of motion on how waves move. Okay, now let's discuss how waves move in different mediums. So something that's important to know is that waves velocity changes based on its medium or wave speed. So wave speed depends on medium. Some examples of this are like light, when it travels through water, it travels slower, so it bends, or when it travels through glass, it also travels slower, and so it bends. But like when you have sound, the speed of sound depends on like if it travels through like a metal rod or like metal or some solid versus like water versus air. And then you can calculate the speed that these travel at based on some certain characteristics of the environment. And so, like for air, sound travels through air at different speeds and different temperatures. That's not because the temperature affects the speed of sound, it's because the temperature affects the properties of air, which then affect the speed of sound. So, first, we'll look at how fast um, waves travel on a string. So, like if you have a string instrument, the string is stretched with a certain tension, um, and based on what material it is, the wave will travel at a specific speed. So the speed of a wave through a string, so I'm gonna write that here. So for a string, uh, okay, for a string, the speed of a wave is equal to, so v is equal to the square root of t divided by mu. And so t here is the tension that the string is pulled at. So if you have a taut string, it's the tension in the string in newtons. And mu is the linear mass density. And then this is in kilograms per meter. And so that's how much mass there is in the string per length. And so you can just think of it like the density of the string. And then this mu here is just equal to the mass divided by the length. So you could see that V is equal to square root of t times or divided by mass over length, or t times length divided by mass. But that is the speed of a wave on a string. And these are the only factors that impact the speed of a wave on a string. And so if you're given the speed of wave on a string of a wave on a string and you're given the wavelength, you can find the frequency. If you have the frequency, you can find the wavelength. But these are all interdependent. And so the speed of a wave on a string is determined by the tension and the linear mass density. And then based on that, it will have a certain wavelength and frequency. And if the wavelength changes, the frequency must also change to satisfy the velocity of the wave. Now for that's only on a string. If you want to find the speed of a wave, this will be like a transverse wave because the string will be vibrating. Um, Now if you want to find the speed of wave through a fluid, so like a sound wave through air or through water, this would be a longitudinal wave because the fluid's compressing um, or it's moving in the same direction. It's oscillating in the same direction that the wave is traveling in. So like speed of sound through water or air, that is given by v is equal to the square root of b over rho. And here b here is equal to the bulk modulus of the fluid. And so water will have a certain bulk modulus and air will have a certain bulk modulus. And I'm pretty sure that the bulk modulus is related to like the incompressibility of the fluid. And then rho here is just the density of the fluid. And so you see that these kind of have like a similar form, where it's the square root of density or square root of linear mass density, and then another factor on top. And then you can also find the speed of like the speed of a trans or a longitudinal wave through like a thin rod. So this would be like a solid rod, um, thin rod. So like if you took a hammer and you struck the end of a rod and you want to know how fast the sound wave travels through it, um, then V here is equal to the square root of y over rho. So again, rho here is equal to density. And this is just simple mass density. So it's mass over volume. Y here is equal to the Young's modulus. Um, and that's another property of materials. Pretty sure it's stress over strain, which is how much the material, or how much, so it's how much the material compresses based on the, you can think of it as like how much the material compresses based on how much force is applied onto it. And so like for a rod, if you strain is like force over area, and then stress is like deformation almost. But that's just another property of a material. And so, and then density again is on the bottom of this fraction, and that's just how you find the velocity or the speed of a wave through a thin solid rod. And now there's finally another one last special case, and that's the speed of light. So the speed of light is c, and then c is equal to the square root of 1 over the permeability of free space times the permittivity of free space. And these are constants that have to do with electricity and magnetism. Um, and so this is the speed of light in a vacuum. And if you work this out, this is again equal to roughly 3.00 times 10 to the 8 meters per second. Okay, and one more thing I want to mention, that the speed of sound through air, so speed of sound through air, I'm pretty sure this is at about 20 degrees Celsius, is going to be roughly 343 meters per second. And you see here that like the speed of light is about 1,000,000 times faster than the speed of sound. And that's really crazy, but that's like how you know when you have like a thunder strike and you can tell, or like a lightning strike and you can hear the delay of thunder. That's how you know, like partially why you can tell how far something is by the delay of how fast you see the light versus how fast the sound gets to you, is because their speeds are so far apart. And 343 meters per second is not slow, but 300 million meters per second is almost incomprehensibly fast. Okay, so now that we've found the speeds through different mediums, what happens when a wave changes mediums? Well, when passing through mediums, so when changing mediums, so frequency always remains constant. And now you should try to see if you can convince yourself why this is true. So why the frequency of a wave must remain constant regardless of what medium it travels through. And so like if you have like a sound that's going at a certain frequency, you can imagining it, or you can imagine it vibrating or oscillating back and forth at a certain rate. Now when it hits like another medium, so at the boundary, it's still going to vibrate or oscillate at that rate. So it'll vibrate that new medium at the same rate. So it makes sense that the frequency will remain constant. But since frequency remains constant, you know that V is equal to frequency times wavelength here. If frequency remains constant and velocity changes, then you know wavelength has to change because this has to be true. And then velocity is determined by like some of these equations up here. So the wavelength changes based on medium, and wavelength changes, velocity changes, and then the amplitude also changes. Um, and this makes sense because like if you're going from a lighter medium to like a heavier one, so like less dense to more dense, the more dense one will have more inertia, it will be heavier, so it'll be harder to move. So it makes sense that like the amplitude will decrease as you go from heavier to lighter. I mean lighter to heavier. And then energy too. So like wave, I mean, amplitude is associated with energy, but like something heavier moving with one amplitude is going to have more energy than something lighter moving at the same, or going at with the same amplitude. So it makes sense that amplitude has to change to conserve energy. Okay, now let's go discuss the interference of waves. So wave interference. Waves follow the principle of superposition. So superposition shows up throughout physics a lot. Like you can have superposition of different forces, superposition of like states, like quantum states, or like things like that. It's just everywhere. But in this case, we're talking about superposition in that the effects of waves are additive. So the independent effects are additive, which means that you can consider the effects independently and just add them together in the end. What does that mean? So let's just say you have a wave that's like this, and it's traveling this way, and then you have another wave here that's like this, and it's traveling this way, and they're the same amplitude. What happens when they meet up? Well, when you add them together, so once they reach the same spot, one wave will look like this, and another wave will look like, sorry, I'll draw this better. Another wave will look like this. Now imagine those are aligned. Now by superposition, since you can add the effects individually, you see that they're equal and opposite. So that means that if you add these together, um, the resulting wave is just a straight line. So when these meet together, oh wait, sorry, this is kind of backwards. When you have a wave that's like going up like this, and then you have another wave that's going down like this, and they're traveling, and once they meet up by superposition, if you add the effects of the waves independently like this, they'll just cancel out. And so what this will look like is so the wave will look like that. So this bump or like this pulse will be traveling one way and this pulse will be traveling the other way. And then when they meet up, it's just going to be flat. And then after they meet up, they're going to I'll do this back. They're going to keep traveling in their original directions. And so they'll meet up and cancel out, or their effects will cancel out, and then once they pass each other, they're going to keep going in their original directions. Um, you can think about it like because of inertia. So what superposition means is again you just add the effects of the waves independently. So in that first example that I accidentally drew, when you have waves that look like this, so when they're traveling and they're both going upwards like that, when they meet, they are just going to you're just going to have two waves that look like that, that look identical. And so that results in a wave that's just twice as high. And then after they meet, so after they pass each other, they're just going to look the same, but they're just going to be going in opposite directions now. And now it doesn't have to be this extreme all the time. Like let's just say you have one wave that looks like this, and then you have another wave that's in the opposite direction, but like half the amplitude. Actually, let me draw this more exaggerated so it's easier to see. Let's just say you have this really big wave coming through, and then you have another wave that looks like that. And so this is half the amplitude. And now if you add them together, you'll just get one wave that's half the amplitude in the upwards direction. So like this wave partially cancels with the bottom wave, and you get that. Superposition is just when you add the effects like that separately. And so you can consider each wave individually and add their effects at the end to get the final wave that you'll see. Okay, now let's move on to wave reflection. Okay, so reflection. Let's say you have a string here, and then it's tied to a wall. So one end of the string is fixed. Then you send a pulse of the string there towards the wall. What will happen when the string hits the wall? It's not just going to stop because the particles all have inertia, and we're going to assume that energy isn't lost. So the wave will reflect off the wall. But if one end is fixed, then the wave will reflect off the wall and be inverted. And so this wave, after it reflects, it will invert. And there's some animations online that can show you how this happens. But if one end is fixed, this wave will invert. And so one way or application of this is when you have a wave traveling through different mediums. So let's just say you have a light string here and you have a wave traveling on this. So this string is light or less dense. And then it meets up with a heavier string here. So this is heavy or more dense. Now this wave isn't just going to pass through completely to the heavy string. You can think about it like partially like this heavy string almost acts like a wall in some way. So because it has more inertia than this light string, and so it partially acts like a wall. So this end doesn't move as freely as if it was all a light string. And what happens then is part of this wave actually gets reflected by the heavy string backwards. And then part of the wave continues on with a heavy string, but at a decreased amplitude. And if you remember before, since the linear mass density is increased, so u is greater, the velocity is going to be less. And since the frequency is the same, it means wavelength is smaller. So this wave, it'll have a smaller wavelength, and it'll have a smaller amplitude because of conservation of energy. But part of this wave will get transmitted. So this is the transmitted part of the wave. And then part of this wave will get reflected backwards because again, this string is like it's almost hitting a fixed wall or a fixed end. And so it gets partially reflected. And it acts as if this is like fixed. So this end of the string is almost like it's like almost fixed to a wall, but it's not really a wall, so it's not fully reflected. But by conservation of energy, again, since it's not fully reflected, part of the wave gets transmitted through, part of the wave gets reflected and inverted because it acts like a fixed wall. Okay, so now what if we have a string that has a free end? And so remember, this is fixed end. If we have a wave traveling on a string with a free end, when it gets reflected, it's not going to invert. So with a free end, again, there's animations online that can show this. When the end of the string is free, the wave or the pulse does not invert. And so the application of this is the opposite of above. So when you have like a pulse traveling from a heavy string or a denser string, so heavy to light, this light string has less inertia than the heavy string. So it doesn't make sense that it would act like a wall. This end would just basically be free. So once the wave passes through this medium, it's like a free end, and so this wave will get reflected backwards partially, and part of it will still be transmitted. Again, by conservation of energy, like you can't have it. It's not going to be fully reflected or fully transmitted in this case, but and then the amplitudes are also determined by conservation of energy. But what happens is you have a smaller wave that gets reflected backwards, and it's not inverted because this end acts like a free end. Again, because this provides less inertia, so it doesn't act like there's anything fixing this end in place. And then this wave gets transmitted through. So this is the transmitted wave, and then this part is the reflected wave. And going from heavy to light, it acts like a free end. And then notice here that this wavelength increases because the velocity will increase since linear mass density decreases. And since frequency is the same, wavelength has to increase. So this wavelength increases, and then velocity also increases. But then again, you have partially reflected wave that's not inverted and a transmitted wave. Okay, now let's move on to standing waves. So from up to this point, all the waves we've seen have been traveling in a direction. But if you look at a string, like on a string instrument like a violin, you pluck it and the wave's not like shooting off in one direction back and forth. You just see it vibrating back and forth. Or it's not going in like one direction. You just see it vibrating back and forth perpendicular to the string. And that's a standing wave. So standing wave. And a standing wave just looks like, so if this is the equilibrium position, you have a wave that oscillates back and forth around the equilibrium position, but it doesn't look like it's moving. So if you look at it over time, it'll seem to trace out like this bumpy pattern where it's like it oscillates back and forth, but it doesn't look like it's moving anywhere. And so, again, this is hard to draw with like a still picture. Oh, this is kind of bad. Let me retry this. Retry that part. So it's hard to draw with like being still, but I'm just tracing out like the different possible positions of the wave right now. So it'll oscillate back and forth. And again, if you ever see a string instrument, it'll form like these humps. So like these are all possible states of the wave. No, it's kind of bad. Let me try to redraw this part. So like it'll oscillate back and forth, and it'll seem to be like just staying still, and not moving. And again, if you look at a string instrument, or this is much better illustrated with a video, you pluck it, you don't see like the string traveling or shooting off. It's just vibrating back and forth. And that's a standing wave. And now standing waves, you have points here that look like they're pinched off or like that they're not vibrating at all. And these points here, they're called nodes. So these are nodes. And those are the points that don't look like they're moving. And then there will be points here, or there'll be sections where it looks like it's vibrating, those are the parts that look like they're vibrating. And those are called antinodes. And then that's where the maxes and mins of this standing wave are. Um, and now standing waves aren't actually waves that aren't moving. They're happen when there's interference of waves going with the same amplitude and same speed, but in opposite directions. So, like if you have a wave that looks like this, and it's traveling in this direction, and a wave that looks like, so same wavelength. So, like if you think on a string, and if you pluck it, it'll obviously have the same wavelength and the same speed since it's in through the same medium. But once it gets reflected, it'll be going in opposite directions. And so by superposition, we see that, like in this state, this wave will just look like that, right? But then let's just say this wave travels a little bit. And so like this top wave travels with the same velocity as the bottom wave, but in an opposite direction. So once the top wave travels a bit, it might look something like this. And once the bottom wave travels a bit, um, it might look something like this. So um, they'll like perfectly cancel. And then so your wave will look like a flat line. And then once this top wave travels again, it might look like that, and the bottom wave will travel in this direction and it'll look like that. and then this wave will then be a reflection of the original. But then this way you can see that there's points where this wave doesn't seem to be moving. So the interference is also always destructive, which means it always cancels out. So this interference here, um, interference at like at these points, well, they're at 0 right now. But like at these points, they're always going to be 0. Oh, I accidentally erased that. Um, So like these are always going to be zeros, or crossing the equilibrium position. And so these are where the nodes are at. And so these always experience destructive interference or where it cancels out. So in these interference ones with superposition, when they cancel out, it's called destructive. And when they add together, um, like this, it's called constructive. But with standing waves, there's points where they always are destructive or are 0, and so those are going to be your nodes. You see, they never add up to, so like the amplitude is always 0. And there's points where they're constructive, where like where the waves are constructive, and they can be constructive in different directions. Like this, they're constructive downwards, whereas here it's constructive upwards. But the places that experience constructive interference, um, are your antinodes, and that's why they vibrate. And then again, if you look up like an animation online of like a standing wave and interference that produces a standing wave, you'll see it's just two waves of the same wavelength, and same amplitude, same frequency, traveling in opposite directions. And they, since they're traveling in this with the same velocity in opposite directions, it works out to where there's points that are always constructive like this, and points that are always destructive, and it creates a standing wave. Okay, now let's review or let's introduce resonance and harmonics. And so this again is has a really strong relation to musical instruments. So resonance and harmonics. Let's just say you have like a guitar string or a violin string or like a cello string or something. It doesn't really matter. The string is fixed at both ends. So you have a string that's fixed at both ends, and then you pluck it. You know that it's going to vibrate like this, where the widest part is going to be at the center. So it's going to vibrate around the center like this, and it'll vibrate back and forth around the center. And so it'll be like, it'll vibrate back and forth around the center. And now that should seem pretty intuitive, right? Now, why isn't this maximum here, like if you pluck it, you know that it'll vibrate back and forth. Um, this is one bulge and one wavelength, or it forms one bulge. So there's an antinode at the center, and there's two nodes at the ends. And the reason there's two nodes at the ends are because the ends are fixed, so they can't vibrate, so they have to be nodes. So when you have a standing wave on a string like this with two ends fixed, you know that the ends have to be or nodes, and then there has to be an antinode in the middle. You can't just have like a random node here, and then this part be like antinode or in between, because it's fixed, so it can't vibrate, so it has to be an antinode. And so you can think of it like if you have a certain section of string or a certain section of tube for like a wind instrument, there's only certain wavelengths that can fit on that string and have like a complete like node or antinode. So where it like satisfies the condition where the two ends are either nodes, antinodes, or one end is a node, one end is an antinode. So like for a string with both ends fixed, it will vibrate with something like this. So the only wavelengths that fit are where, I don't know, I can't write a G. Only wavelengths that fit are where both ends are nodes. So string with both ends fixed. You can also have like a tube here, like I said, with wind instruments, and you know the tube, both ends are open here. So you know that they can't be nodes because both ends are vibrating like back and forth with a longitudinal wave. And so when you have a wave here, it'll fit in the tube like this. So it'll vibrate back and forth across these positions. And so there'll be, so for this one, you have node, node, antinode. And for a tube, you have node in the middle, and then antinode, and then antinode. Because when the tube's ends are open, you know that the ends have to have air that's vibrating. And so they have to be antinodes because the air is moving back and forth as it enters the tube. And so the both ends of this tube have to be antinodes. And then so the middle of the tube has to have at least one node. And again, this is how like a wave can fit inside a tube. You can't, like for a string here, what do I mean by fit? Well, let's just say you have a string. You can't have a wave that like extends like outside of the string. You know, that doesn't make any sense. Like the end of the wave or like the node of the wave has to be at the end of the node of the string. Like it can't go outside the string, past the string, or it can't go like halfway in between, or like not halfway, but like some random place in between the string, because this the string is fixed at this point, which means the node also has to be at this point. And the same reasoning applies with the tube, except it's with antinodes instead of nodes. And then with tubes, you can also have the case where one end of the tube is closed. So, like if you have a cap on one end of the tube, then it's closed. And what that means is that there has to be a node there. Because if the tube is closed, air can't vibrate there because there's nowhere for it to vibrate to and from. Like they can't go past this closed end or into this closed end. And so that part has to be an antinode. I mean, it has to be a node. So what a wave in a tube will look like with one end closed is that will be an antinode, and then it'll oscillate between like these states. That kind of looks. I'll draw it a bit shorter so it's easier to see. And then I'm drawing these waves as longitudinal, I mean, as transverse waves, but like for sound, realistically, they would be um, longitudinal waves. So the wave here, it would fit like this, where the closed end of the tube is at a node, and then the open end of the tube is an antinode. And now what I've drawn here are the fundamental frequencies or the fundamental tones of all these three setups. So now let's explore each one by one and see what I mean by fundamental frequency. So now when you have something with two fixed ends, like a string here, so both ends are fixed. They can't move. When you have two fixed ends, then those ends have to be antinodes. I mean, they have to be nodes, sorry. So two fixed ends, that means ends must be nodes. Now let's think, what is the largest wavelength that can fit in between this? So that what is the largest wavelength that will produce a wave, standing wave, so that there's two nodes here? Well, if we extend this wave forward, we'll see that a wavelength is where it repeats. So if this is one full wavelength, we'll see that this section is actually half a wavelength. So if you have a string that's length L here, L is equal to 1/2 of the wavelength of this fundamental frequency. So the lowest frequency that can produce a wave that satisfies the condition of two fixed ends, where there's nodes at both ends, we'll have a wave that looks like this, where it oscillates with two nodes and one antinode. And then the length of the string is equal to half of this wavelength. And we'll call this, this here, sorry, we'll label this the fundamental tone or the first harmonic. And then this is the fundamental frequency. This is the fundamental wavelength. The frequency, let's just call this F. Maybe you can write F subscript 1. This is the fundamental frequency. And this is the frequency again. It's the lowest frequency where a wave will, you can say, where the lowest frequency where the wave fits on this string with two nodes. Now, here is something interesting. This isn't the only way you could have two nodes at the ends. Let's just say you have a higher frequency, and the frequency is high enough to where your standing wave looks like this. So you have like these two bumps here. Notice that there is still a node on both sides, so both ends are still fixed. A node, but then there's an extra node in the middle, and then there's two antinodes here. Now, a string can still vibrate with two fixed ends like this because both ends are still nodes, you just have another node. Notice now that the frequency is double what it was before and the wavelength is half of what it was before. So for this, we'll say n equals 2 because this is the, you can fit two of these antinodes on one of these lengths. So for here, we'll call this n equals 1, or this is the fundamental tone or the first harmonic. The second harmonic, this would be the second harmonic here. So this is second harmonic, or the second overtone. And this just means that you have like two of these, you have two of these fitting on this one length. So you have two antinodes fitting on this length. And then you could also have like an n equals 3 case. So what n equals 3 would look like is you have three antinodes. So it would be something like that, where you have three antinodes and two nodes. And then you could n equals 4, n equals 5, n equals whatever for two fixed ends, as long as it's an integer. And now the frequency of this nth harmonic is going to be equal to n times the fundamental frequency. Notice that the frequency of this n equals 2 harmonic is going to be double the frequency of the fundamental frequency. And so for this, f of 2 is equal to 2f, and f3 is equal to 3f. And that makes sense because you're fitting 3 times as many oscillations per length. And the velocity stays the same, so the frequency has to increase. And then the wavelength here, because the wavelength decreases, the wavelength here is the nth wavelength, is equal to this original wavelength divided by n, because it's the same length, but you're fitting two of these waves on there, or like two of the original on there. And so for the second harmonic, the wavelength is going to be half of this first harmonic wavelength. And for the third harmonic, the wavelength is going to be a third of this first harmonic wavelength. And then the total length here, so this total length L is equal to n divided by 2 times the nth wavelength. It might be clearer if you write it as n times the nth wavelength divided by 2, because each of these like bumps here is half of a wavelength. So it's the wavelength divided by 2, and n is the number of antinodes or the number of bumps. So the total length of this section is equal to the nth harmonic n times the wavelength of the nth harmonic divided by 2 for two fixed ends. So again, this is like a string where both ends are fixed. Now let's consider the case where you have two free ends. So this is like a tube where both ends are open. And this is basically the opposite of the string, except you have nodes instead of antinodes. So if you have two free ends, that basically means that you have to have two antinodes at the ends because the ends have to be vibrating. So you have two antinodes. And the lowest frequency that can produce two antinodes here is where you have two antinodes at the end and one node here in the middle. And you notice that this is just the opposite of this, where you have one antinode in the middle and two nodes at the end. And so when you have two free ends, it's the same, but you have antinodes. You must have antinodes at both ends. And so the fundamental frequency here is, again, this is half a wavelength, because if you trace this out here, a full wavelength is going to be that. So this section here is only 1/2 of a wavelength. So L, the length of this whole thing, so the length of like this tube here, L is going to be equal to this fundamental wavelength, or like the wavelength of this fundamental frequency divided by 2. Okay. And then the same equations hold. So if we look at like this is the fundamental tone, or the first harmonic. If we look at the case of so this is n equals 1. If we look at the case of n equals 2, again we must have antinodes on both ends. I'll draw it a bit bigger so that it's easier to see. You have antinodes on both ends, but then now you can have like an extra antinode in the middle here. So if you have an extra antinode in the middle, it still satisfies the condition that there's antinodes on both ends, but now the wave will look something like this, where it's like that, where you have antinodes, you have 3 antinodes and now 2 nodes. And then if you have n equals 4 or n equals 3, it'll be the same, but then you have 2 antinodes in the middle now. And then so it'll look something like that. Yeah, sorry, that's like it's really not even, but it was just that's like the general shape of it. And then you can go on for n as large as you want, as long as it's an integer. And so again, like I said, the same equations apply. So the frequency of the nth harmonic is going to be equal to n times this fundamental frequency. And so if this frequency is f, so if this has frequency f, this would have frequency 2f, and this would have frequency 3f. And then the wavelength of the nth harmonic is equal to this original wavelength divided by n. So if this wavelength up top here was lambda, then this wavelength here is going to be, so again, this here is going to be 1/2 of the nth wavelength, which means that this total wavelength here is going to be wavelength. So since you can fit 2 of these waves in the same space it takes to fit one of these old waves, this wavelength of the nth harmonic is going to be equal to the original wavelength divided by n. So you see the wavelength is the original wavelength divided by 4 in this case. So this is still, this part, this section here between antinodes is still 1/2 of a wavelength. But then since you can fit 3 of them instead of 1 of them on this total length, this will be the original wavelength divided by 3. And then the length here, this total length, is just going to be equal to n times this nth wavelength divided by 2. Because again, this is half of a wavelength, and if you have the third harmonic, you can fit 3 of them on there. So L here is equal to 3 times this third harmonic wavelength divided by 2. And this mirrors the two fixed ends equations above. And now we have one last case where you have one free end. And then again, this shows up when you have like a tube here where one end of it is closed and one end of it is open. And so what that means is that you must have one node at one end and one antinode. And so what that looks like is if you have an antinode here and a node here, the smallest frequency that allows that to happen is something that looks like this, where this is an antinode and the wave oscillates here, and then it's a node at this end. And so they'll oscillate between like these different states here. But again, it only occupies one state at a time. I'm just drawing out the different possibilities for where the wave is. Now, if we extend this out, we can see that this here, so this here, oh, that's kind of a bad drawing, but if we extend this wave out, we can see that this is one full wavelength. And then this here is going to be half a wavelength. So we see that this is actually only 1/4 of a wavelength. And so if we label this distance L, which is the distance between the two ends of like, well, it's the distance between the two ends, L, we see that up here we have L is equal to wavelength divided by 2. But here, with one end free and one end fixed, L is equal to 1/4 of this base wavelength. And now, here's another thing. So this here is the n equals 1 harmonic. What happens if we try to do an n equals 2 harmonic? Well, we know that for a harmonic, the frequency doubles and the wavelength halves. So the wave would look like this. But then, wait a second, we have one end fixed here, but then this is now also a node. So now we have two nodes, but we know that we need one end to be an antinode. So this cannot work with one end free, so one fixed end. You can't have an n equals 2 harmonic with one fixed end, because that would mean that there's two nodes, but you need one side to be an antinode. So you can't have an n equals 2 harmonic. But what about an n equals 3 harmonic? Now again, the frequency is triple the original. And so what that would look like is you have another node here, and then it would look like this. So notice that you have two antinodes and two nodes. But then this still satisfies the condition that one end is free and one end is fixed. So an n equals 3 harmonic is possible. And notice now that, again, this still follows the same equation before. The frequency of the nth harmonic is just equal to n times the base fundamental frequency. Because as you see here, Oh, and then the wavelength of the nth harmonic is equal to this original wavelength divided by n. As you see here, the length, you can fit 3 of these original ones into this new third harmonic, but the length is the same, so the wavelength has to be 1/3 of the original, which means the frequency has to be 3 times the original since the medium didn't change, so the velocity has to stay the same. But then you can see that the n equals 2 harmonic isn't possible. And if we think about the n equals 4 harmonic, that's also impossible, because it would also result in a wave that looks like this, where you have you have 3 nodes, but you have 2 nodes on the ends. So n equals 4 does not work. And then in general, you can see that with one free end and one fixed end, so you can only have odd harmonics. When you have one end that's free and one end that's fixed. So only odd harmonics are possible, but then the same formulas apply. So these don't change for the frequency and wavelength of the harmonic, but you cannot have even harmonics. And then finally, when this is length L, you have L is equal to n times the wavelength of the nth harmonic divided by 4 instead of 2, because you see each of these is equal to the wavelength divided by 4. As you see at the start here, this is 1/4 of a wavelength. So the third harmonic is 3 times 1/4 of the wavelength of the third harmonic. So the total length is going to be the nth harmonic times the wavelength of the nth harmonic divided by 4 instead of 2 as in above. And so those are how harmonics work on things with 2 free ends, 1 free end, and 2 fixed ends. All right, that is a overview of physical waves and their properties and how they work, including their harmonics, standing waves, reflections, moving through mediums, velocity, things like that. All right, so thanks for watching.